Right, so we've already seen Ampere's law. Remember, Ampere's law says that an electric current makes a magnetic field. Now this integral expression here is basically telling us that the magnetic field, if we have a single wire as a source, the magnetic field will have a circular form to it. Now there is an issue with Ampere's law which makes it incomplete, and Maxwell realized this. Let's say we have a battery here, and let's just go ahead and build an RC circuit. Let's go ahead and throw, let's go ahead and throw a switch in here too while we're at it. So there's our switch, resistor, and then importantly the capacitor. All right. Now the idea goes like this. Let's say the capacitor is initially discharged, and I go ahead and throw the switch. Now we know at time 0 the capacitor will act as if it were a wire. It's not actually a wire. No current is flowing between the gap here, but we'll have current flowing as if we could replace the capacitor with a wire just for the split second when we close the switch. Now after that we start to build up charge on the capacitor, so we'll note that we're going to start putting up a bit of a charge here, plus Q, minus Q there. And this charge will keep increasing as a function of time until finally the current exponentially decays down to 0, and the voltage across the capacitor at that point will be equal to the battery EMF, and so this will converge to C times the battery EMF. Okay. That's all well and good, but what we're really interested in right now is a concern that Ampere had with this. His thought was, well, let's say I want to know the magnetic field, say right here. Now we know that our current is going to be flowing like this, and so by the right-hand rule we know that we should get a magnetic field line that's coming, that's coming out of the screen right there. And a matching spot over here, it would be going into the screen. Sorry for the clutter. Okay, so we can move that. Nope. Okay. So that's good, and we can find the strength of the magnetic field using Ampere's law, but there's a subtlety here. Let's go and look at our capacitor more carefully to see what that subtlety is. So I'm going to draw a really big capacitor, like so. And again, let's say this is the point right here where I want to know the magnetic field strength as we're carrying our current I through the wire. Now because the capacitor is an actual physical break in the circuit, no current will be flowing across this gap in normal operation unless the voltage gets so high that we have dielectric discharge and we arc across the capacitor plates, but that's not what we're thinking about right here. Okay. So the prescription by Ampere's law is we go ahead and pick an Amperian path, and I'll attempt to do a really bad job of drawing my Amperian path in 3D here. So over here the magnetic field vector would be going in, over here it would be going like so, etc. And everywhere here the magnetic field strength would be a constant. And so the idea is we can go ahead and write Ampere's law, integral B dot ds equals mu naught times I through. Okay, in this case I through will just be the conventional current going through here. But the subtlety is this. How do we count the current going through the Amperian path? Now, this means that the current actually has to flow through some surface that's bounded by the path. Now, the natural thing to do would just be to say, well, okay, if we imagine the circular Amperian path as, say, being the clamp on a drum head or something like that, the natural choice of surface would be the drum head. Okay, that makes sense, and if we do that, we would be able to take this through and say, okay, so integral b dot ds equals mu naught. Now I through is just I, and we can go ahead and evaluate integral b dot ds to realize this is integral b times ds, because b and ds are always following each other. The ds follows the orientation of my Amperian path. So there's a ds right there. And since the magnetic field strength is a constant, I can pull that out of the integral. And this will evaluate to 2 pi r, where r is the radius. So this will be b times 2 pi r equals mu naught I. And so finally we can write that b is mu naught over 2 pi I over r. And that is for our choice of purple surface. Now, you might think that that's the only choice of surface that we could do. Unfortunately, you would be incorrect. Mathematicians assure us that in order for calculus to not break, this can't work for just for one specific surface bounded by the Amperian path. It has to work for any surface that I could possibly imagine going through that same Amperian path. So for instance, I could instead pick, pardon really bad 3D drawing here, I could instead pick some kind of a crazy Amperian surface. Imagine that this is descending down behind and in front. Basically think almost like a hamburger bun with a hole drilled in the top. You know, the surface of the hamburger bun with just a hole drilled in the top where the Amperian path is. We follow this surface all along and then get back over here. Let's just draw it a little more lame, and that might help. So what I'm imagining here is, say, a cylinder, kind of a shaped surface that's cutting through here between the plates like so, something like that. We can extend this off all around. Something like that. Again, apologies for the horrendous art here. I know it's bad. But that's the idea. As we go ahead, we imagine just basically like a small squat cylinder kind of shape. Just drill a hole out at the top where the Amperian path will sit, and then we use the rest of the surface. Okay, now the key trick here is no current's going through the surface here, and also no current is going through the surface here between the plates, right? Because we're in normal operation, we're not arcing. So if we start over here again, so we'll say, okay, integral b dot ds equals mu naught times I through. Here, I through is just plain 0. So we get that b is equal to 0. And that's what we would conclude using Ampere's law on the orange path. Now, Maxwell realized that this was a problem. Physics has to be consistent. It should, since mathematicians tell us that this integral, shouldn't matter what surface we choose, as for the same Amperian path, we should get the same answer no matter what. So Maxwell tried to think, is there something that is proportional to the current that would be between the plates? And he realized, yes, there is. Because if we look between the plates, so let's draw another capacitor here. If we look between the plates, so at some instant we have charge plus Q here, minus Q here. He realized that the electric field strength, or more properly in this case it'll be the flux, the electric flux between the plates was proportional to Q. So then he realized that the current for our, in this case, has to be proportional to dq dt. So the current here would be proportional to the time rate of change of the electric flux between the plates. So Maxwell's idea for how to fix up Ampere's law would be to add a term right here. So we'll just go ahead and imagine adding a, let's go ahead and imagine adding a term right here, some sort of a fudge factor that, not right there, adding a term right here, some sort of a fudge factor that this term would be equal to this term when we choose the orange surface for our counting the current for our Amperian path. Okay, so let's work out what that would be exactly. As a quick review using Gauss's law, we can zoom in on one of the plates like so. Let's say it's the upper plate. So we'll have right on the surface, positive charge right on the surface, like so. So this will be our charge plus Q. And we'll have electric field lines exiting through here. We're starting on the surface and exiting off. Okay, let's just go ahead and use Gauss's law to figure out how to tie our flux over to the current. So Gauss's law is going to require me to choose a Gaussian surface. In this case, the Gaussian surface will be a pizza box shape. So the idea goes like this. On the edges of the pizza box here, and in front and in back, the electric field is either 0 or it is perpendicular to dA, because remember here that dA would point out like that and out like that. So if E is pointing down and dA is right or left or in or out, the dot product would be 0 if we happen to choose this through an area where there is an electric field. Now this top surface here, there is no electric field because it's a conductor in equilibrium. Well, equilibrium-ish. So this just leaves this surface right here. So let's go ahead and do Gauss's law on that. So it'll be integral E dot dA is equal to the charge enclosed over epsilon naught. Okay, well in this case the charge enclosed will just be Q. And again, this will be the same deal. E dot dA is just going to become E times dA. So this will be integral E times dA. And then again, we can pull the E out of the integral, E integral dA. Integral dA is just A, so we have EA equals Q over epsilon naught. So we get that E. Whoops, and actually that's good, because EA is the electric flux. Okay, Now what we want is something that I is equal to. So we'll solve this for Q. So Q will equal epsilon naught phi E. And then I was equal, we observed was equal to dq dt. Well, epsilon naught's a constant, we can pull that out. So it'll be epsilon naught d phi E dt. Okay, so now this isn't actually saying the current, that this is a current. It's not. We are just observing that this quantity between the plates is equal to the current in the wire that connects to the plates. But for historic reasons, we define this quantity, epsilon naught d phi E dt, as the displacement current. Now, displacement current is an absolutely awesome name, except for two small details. One, it's not a current, and two, there's nothing being displaced. The name is an accident of history, dating back to a much earlier model of electricity and magnetism that was based on the idea that light was waves in a substance called the luminiferous ether. The electric and magnetic field were modeled as in part as vortices in this ether. And in this picture, that name made some sense. That name does not make any sense anymore at all. But physicists sometimes get a little lazy and they just leave it like this. So we can rewrite the Ampere's law now as the Ampere-Maxwell law. This is Maxwell's contribution to it, to say integral B dot ds is equal to mu naught times I through plus any displacement current that goes through our surface. This turns out to be the correct and complete expression. More normally, we're not really that big a fan of referring to the displacement current anymore. And so usually now we write the Ampere-Maxwell law more like this. Integral B dot ds is equal to, distributing mu naught out, mu naught I through, plus, we'll put in what I displacement is, that epsilon naught d phi E dt, mu naught epsilon naught d phi E dt. This is actually probably our preferred version, but for certain problems, as we'll see, it's useful to keep the fiction of the displacement current around, just because it can make it a little easier to think about. So, a quick note here is that this combined with Faraday's law, it turns out that the two of them taken together will have the form of a wave equation, where the speed of that wave will be 1 over the square root of this number, of this product right here, which turns out to be equal to the speed of light. Now, let's focus more on what the Ampere-Maxwell law is telling us here. So again, we're saying a way of making magnetic fields, ones that are kind of circle-ish, will be due to either having moving electric charges, or by having a time-varying electric flux. Usually it's a time-varying electric field, but a time-varying electric flux. Okay. So let's follow this through just with an example for how this would work with our capacitor. So going back to the issue with our capacitor, way up here, if we go and take this surface here, now let's see what our Ampere's law statement will look like. our Ampere-Maxwell Law statement. So now we'll use the Ampere-Maxwell Law. Will now say integral b dot ds is equal to mu naught times I through, and here it will be useful to use the fiction of the displacement current plus I displacement. So going back to this here, if we use the purple surface, we have a physical current going through the purple surface, but no displacement current. If we go through the orange surface, we don't have a physical current, but we do have the displacement current going through between the plates. And that displacement current was constructed to be exactly equal to the current. So either way now, we predict that the magnetic field strength that we get for that example will be mu naught over 2 pi times I over r. And that is indeed correct. We have done the experiments and it does check out. But we get a new fun prediction as well. If we take a look at our charging capacitor some more, so plus Q minus Q. If we look at our charging capacitor some more, we can take this idea a little further and say, okay, we're building up an electric field like so. And if the magnetic flux is increasing, then we can model this as saying that inside the plates we have a downward displacement current going between the plates. So now this means I can pick a point like, say, right here, and right here I should again have a magnetic field going out of the page, inside the plate. Even outside the plate over here too, there should be one. And again, these will be, the magnetic field lines will be circles. So attempting to draw in 3D, something like that, and something like that. Okay. Well, for this case here, and for picking points that are right between the plates here. So for this case here, we can go ahead and make our Amperian paths follow the magnetic field lines. That will be the standard prescription. And if we do this one right here, when we go and take a look at our surface here that's penetrating right through the middle, so we'll do the case here. We'll say this is radius little r. Oops, sorry, radius little r. And we'll say that the capacitor plate has radius big R. So if we do this one here for the outer case, so now again I'll have integral b dot ds equals mu naught times I through plus I displacement. Now here I through is 0, but I displacement will be equal to I, the current, the inbound current onto the charge, inbound outbound current through the wire here. And by the same prescription, it's going to evaluate to b times 2 pi r, little r in this case. This will be mu naught I, and we'll get again that b is mu naught over 2 pi I over r. And sure enough, even in this region right here where there's no current nearby, if we go ahead and stick a Gauss meter here, we measure a magnetic field. Okay, now let's go look instead at this inner magnetic field line. So again, same idea. Integral b dot ds is equal to mu naught I through plus I displacement. And by the same prescription as before, the integral will evaluate to b times 2 pi r. And we will get that I through is equal to 0. But now we got to look at the displacement current more carefully, because all that's going to count is the displacement current that goes through there, that's right inside that magnetic field line. So let's go and take a top-down picture on this. So I'm imagining my eyeball right here. Man, that's the world's longest eyelash. Much better. So imagine my eyeball right here looking straight down from on top. Okay, so if we do that, my capacitor plate is going to look something like that. And now the displacement current is going to be spread uniformly throughout between the plates. So the entirety of this displacement current will be equal to I, what we've constructed it to be. But our magnetic field, so here's our, oops, there's our magnetic field line. It's just a loop that closes back on itself. Our magnetic field is going to be here, and I'm only interested in the displacement current that's in there. Okay, but we can set up a proportion. We can observe that that displacement current, the ratio of the displacement current inside here to the entire displacement current, which is equal to I, that'll be equal to the ratio of the area of this circle, which is 2 pi little r, sorry, pi little r squared, to the area of the capacitor plate, pi big R squared, and we can cancel the pi's. All right, so we get then that the displacement current is I times R squared over R squared, and now we can take that and substitute it back up into there. All right, so we now have B times 2 pi little r is equal to mu naught I times r squared over r squared. We can cancel one of those r's, divide through by 2 pi, and now we get that the magnetic field strength inside is equal to mu naught over 2 pi times I times r over r squared. And it turns out that if you stick in a sensitive enough probe and actually look, this is exactly what we get. So it does all check out. Okay, so I hope that you found this example helpful. Like I said, the one other thing that we will observe here is that we can make a magnetic field by either a moving charge or a time-varying electric field. And if we combine that with Faraday's law, that says we can make an electric field with a time-varying magnetic field. The two of those combined together are a wave equation for a transverse electromagnetic wave that propagates at the speed of light. And indeed, it turns out that that is the nature of light.